So just to have a look at how the images look like. So you can see the original image and the histogram, the corresponding histogram, and then with increased brightness, with decreased brightness, you can see that now the image looks darker generally. And now the histogram has shifted down towards 0, and we have this peak at 0 that is the saturation imposed by this part. Actually, looking at this histogram, can we, or visually at least, can we say that there is a shift that doesn't cause any saturation at 0? Is there a decrease of the gray values that doesn't cause saturation? What about this interval? So this interval, if I subtract, let's say this 35, if I subtract 35, it doesn't seem that there is any pixel that has a value between 0 and 35. So it doesn't matter if I subtract 35. So let's say there is no pixel below 35. If I subtract 35, have I lost information? Why?
Because there's no information for the
Yeah. And if I subtract 50? Yeah. And remind always, the concept of information loss is if you can invert the operation. So if I subtract 35, I'm not saturating. So if I add 35, I'm getting exactly the same values. But if I subtract 50, then all these values have to be saturated. And then if I add 50 again, then I don't know, for instance, for some of these pixels with 0 value, I don't know if they were truly 50 or they were 49 or 48 or whatever. Okay? So I cannot exactly recover the same information. You had a question? Okay. Okay. Good. Then more operations, decreased contrast. So decreased contrast is one in which we multiply by a number. Pasa. ¿Y cuánto un chiste anda? ¿Cómo le llamas? Alejandro, cuéntanos algo.
Es que así en frío no se me ocurre ninguno.
No, pero no en frío. Cuando vais subiendo, uy, tarde, voy a ir pensando en un chiste. Porque...
A mí me contaron uno, pero es un poco largo y malísimo.
Da igual.
Vale. Estos son dos ladrones tal, que van a robar un banco, no sé qué y tal. Y había uno que era un poco no muy listo y otro más listo. Entonces, ¿lo sabes?
No, pero me está haciendo
Entonces, están persiguiendo a la policía, tal, van a ir, que no pueden más, tal. Y ahí con la policía pisando los talones y se meten en un callejón y no hay salida en el callejón. Y había un saco de patatas vacío y un bidón. Entonces le dice el listo al tonto, tal, tú haz todo lo que haga yo, no hables ni nada. Entonces se mete el listo en el bidón y el otro en el saco de patatas. Entonces llega la policía, tal, no hay nada y le dicen, con las porras tal, y dicen, vamos a darle a ver si están dentro. Le dan al bidón y entonces dice el que estaba dentro, que era listo. Bidón, ¿sabes cómo suena el bidón? Y entonces le empiezan a dar otro, le saca patatas y hace bidón, y ya está.
Muy bien. Bueno. Okay, so this transformation is multiplying the input image by factor A, but this factor A is smaller than 1, but there is a kind of a small trick here. So this small trick, what does is it centers the transformation at some gray point S. So for instance here, let's say that S is 127. So if you have a gray point, any one of these, and you subtract 127, what you're doing is putting the origin of the gray values at that point. So now this would be 0. Let's say this is 127. So 127 would become 0. Lower values are negative, higher values are positive. Then you are multiplying by a number that is smaller than 1, and then you are adding back this 127. ¿Por qué no chiste, Ana? ¿Cómo que no sabes?
¿Por qué no sé?
¿Todo el mundo se sabe alguno?
Yo no.
¿Tú no?
De verdad que no.
Bueno, pues cuando vais subiendo por las escaleras vais pensando, joder, que llego tarde, no vamos chiste. Bueno, ¿cómo era tu nombre? Perdona.
Marta.
Marta. Okay, so this trick is very much used. So this is a shift, or this is a redefinition of the origin of an axis, and then you apply some operation, and then you restore that origin. Okay, and here is the effect. So now the gray values compress around 127. So in the limit, let's say that A is a very, very, very small number. So then all the gray values would collapse in 127. So now we have decreased the distance between minimum and maximum in this image. So you can see this is the minimum, this is the maximum. You can compare to the minimum and maximum of the original image. And you see that the range is much smaller. So this much smaller range is what is called the contrast. So the contrast is the difference between maximum and minimum. Okay, so this is decreased contrast. If A is larger than 1, then we have an increased contrast. But we have to be careful with saturation, because now we might have that the new gray values are either below 0 or above 155. So we have to pay attention to saturating at 255 and 0. This is what this is doing. So if this is my transformation, if my transformation of a particular pixel at a particular row, column, and arm is smaller than 0, then I saturate to 0. If it is larger than 255, I saturate at 255. And if I'm not overflowing my range, then I simply keep this transform value. Okay, and here you have the effect. So here now we can really see that we have higher contrast than the original. And with this, now the distance between maximum and minimum is larger, and you can see that all these pixels are close to saturation. All these pixels are close to saturation, but now on the dark side. And you can see that originally there were some, for instance, these borders of the windows, they were visible before. Now they are not visible. And now you can interpret in terms of saturation. So here, the borders are there, but now there is much smaller difference between minimum and maximum in that area. So that is, the local contrast is worse now in that area. Okay, good. Any questions so far? No? Okay, so let me annotate that you can do this as part of your practice. So we go to, where is it? Archivos. Archivos, pero no. Aquí. So I think in decreased contrast, we don't have it. So we have brightness, but we don't have contrast. Is decreased. Okay, good. So here we are. And then you can apply a general transformation that is called contrast stretch. So this contrast stretch transforms the minimum and maximum of an input image into some fixed minimum and output, minimum and maximum values at the output. And this is simply the equation of a straight line. We were seeing this transformation in one of the previous classes. So this is simply changing the slope. And for instance, can you tell me, are we increasing or decreasing the contrast in this, or what do we have to look at to know if this transformation is increasing or decreasing the contrast?
Decreasing.
Why?
Because the difference is getting lower.
This difference here, you mean?
Yes.
Okay.
But the range is bigger in the histogram.
Now the range is bigger. So are we decreasing or are we increasing? We are increasing. So actually it has to do with the slope, right? So if the slope is smaller than 1, then it is a decreasing contrast. If it is larger than 1, it is increasing contrast. And this slope is larger than 1. And actually the slope is determined by this ratio. So this ratio here, what is the maximum and minimum in the output image divided by what is the maximum and minimum in the input image. And this one you fix. This is what you are choosing in this transformation. This one is given by the input image. Okay, so and in this particular case, the slope is larger than 1, so we are increasing the contrast. Okay, so then here we have some considerations about information loss when you are adjusting the contrast. So let's say that we have an original image. This is the histogram of the luminance, let's say. And then we have one with lower contrast. So with lower contrast, let's say that the constant that we are using to multiply this A is 1/2, then we are decreasing the contrast, and we understand that the minimum and maximum, they collapse towards the middle of the range. Now we take this one, and we restore the contrast. So we restore the contrast by expanding it by factor 1. So if you, by factor 2. So now you take this one, multiply it with one of these transformations, this one here, but now with a factor 2. And this is what we recover. That is very similar to this one, but not exactly the same. So one of the features is that this one has holes. Why do we have these holes?
Because no puedo. Porque la información se tiene que repartir para avanzar más.
¿Y no podría haberla repartido rellenando los agujeros?
O sea, porque cada vez se la expansión es como por ejemplos, plan por partes.
Pero cada punto es una PA2, entonces cada 2 hay un blanco.
No. O sea, cada punto es una PA2, ¿qué significa?
Que antes tenías, por ejemplo, 100 puntos y ahora tienes 50. Entonces al volver.
No. De hecho, el número de puntos es el mismo. Ah, hace un dibujito. Okay, so let's say that we have an image. And let's put here these values. So let's say we have values 1, 2, 3, 4. So now we construct a new image, and this I prime will be 1/2 of I. So this new image, I prime, draw it in a different color. So this will be the red image, I prime. So now my new image I prime will also have 4 values for this. Sorry. Okay. Bueno. Esto es molesto. ¿Cómo se hace para cambiar el comportamiento de esto? Me parece que es aquí, ¿no? Entrada de lápiz a forma. Pues no. Pensé que era eso. ¿El qué? Pues ya está.
A lo mejor es porque como ya está el cuadro.
Puede ser que como ya está el cuadro, lo que voy a hacer va a ser seleccionar el cuadro.
Pero sin el lápiz.
Selecciono el cuadro y lo borro. Okay, so we have another image of 4 pixels. So it is not that we have less number of pixels. We have the same amount of pixels, but now, because we are divided by 2, we will have the following values. So we have to take a decision of how to handle the rounding. Okay, so let's say that we take the integer part of your. So very typical one is the following. So integer part of whatever value you have there. So this would be 1 divided by 2 is 0.5. The integer part is 0. Then this would be 1, this would be 1, this would be 2. And now we construct a new image that will be the blue one, that is supposed to be like the first one, because we are doing twice I prime. But now we will have 4 pixels in the same way, and now it will be 0, 2, 2, and 4. So if you compare to the original one, we have lost some values. So value 1, we don't get it. Value 3, we don't get it. And the reason is here. So the reason is here. It is because of the 2. Because we are taking integer numbers multiplying by 2, so all these numbers in the output have to be a multiple of 2. So that is why all the odd numbers in the output, they are not represented. Now we apply a further expansion of contrast by another factor 2. So now we are expanding and we are saturating at the borders. And so this is the one with expanded contrast. So we are not representing all the images there, but this is the one with expanded contrast. And now we restore the contrast again by multiplying by a factor of 1/2. And this is what we get. So what we get is similar to which one? To this one, to the second, or to the first? Yeah. So it is similar to the first because it has in principle kind of the same contrast, but because of this saturation here at 0 and 255, we have the same problem that we had before. Okay, so now when we reduce the contrast, we don't have this 0. We don't know all of these pixels with 0 value where they were coming from in the original range. So they will all be mapped to this point. And the same with the saturation of 255. And now we don't have these problems with let's say missing values. Yeah.
I can understand why we use information in the first step.
In this one,
Yes.
because you are now expanding the contrast, but your range of representation is still 0 to 255, and now you need a wider area, but you cannot have negative numbers, so you have to saturate. Is that more clear now?
Yes.
Okay, so here we have all the different images. So this is the original image all the time, and then this is the one with lower contrast. This is the one with lower contrast restored. So this is this one here, lower contrast restored. And this is the high contrast restored, and then this is high contrast, and yeah, you can compute all kind of differences. So for instance, we can compute the difference between this one, the low contrast restored, and the original one. And it looks like systematic or random errors. This is what you would expect from these kind of missing values at the odd numbers. But that's a region where we have systematic errors. So in this region here, probably because they are saturated or they are very close to saturation, we have systematic errors. And here we can compute, for instance, the difference between the high contrast restored and the original. And there is a lot of errors everywhere, and all of those are systematic. And this is what we expect, because here in the high contrast restored, because of the saturation, we have lost a lot of information. So for instance, here we compare this histogram to this one, you have lost all this area, and you have also lost all this area. So we should expect the errors to be in the very dark regions and in the very bright regions. Let's see if that is the case. So this is the brighter region of the input image. Here we have a lot of errors, and the same happens here. And this is one of the darkest areas in the original image. And again, we see here a lot of errors. So some operations are more dangerous to images than some others. So these operations of you decrease contrast and then you increase it again, or the opposite, they are not totally innocent to the images, so they can make bad things to them. Any question? No? Okay, so here you have the gamma transformation that it was introduced at the beginning of the lecture. So I just mentioned that there was a gamma transformation. This is the one. So again, this is a kind of the same trick that we had before. So before we were subtracting a value and then adding that value. So that was shifting the origin of the gray values to a particular point. Now we have the same trick, but now in a multiplicative way. So we want the maximum number to be 1. So you take the input image, divide by 255. So you are sure now that any pixel is smaller than 1. Then you perform some operation and then you restore the original range. So this kind of tricks, either additive, as we did here. So here we did that trick of shifting the origin in an additive way. Now we have play kind of similar trick, but now in a multiplicative way. And in this multiplicative way, we are constraining the range of values to some particular point. Actually, if you think of this transformation in logarithmic terms, let's put it here. So let's move it up. So we have I prime or j in the slide. It was 255, and then I divided by 255 1 per gamma. So now you take the logarithm of that expression, you would have the logarithm of 255 plus 1 per gamma, the logarithm of I minus the logarithm of 255. So it is the same trick. Here we are subtracting s, we are adding s, and we have some multiplicative factor a. So it is the same operation that we had before, that we call increased brightness or decreased brightness. Only that now the operation is performed in the logarithmic scale. But it has the same structure as we had before. Okay, so for instance, if gamma is larger than 1, what we are doing is bending the transformation upwards. So we have here the identity transformation. The identity takes an input value and returns the same value. But now our transformation with gamma larger than 1 is this one. So just question, is this gamma transformation, this particular one, increasing or decreasing the contrast? Is it increasing or decreasing?
Increasing.
Increasing, why?
The slope is bigger.
Everywhere, the slope is bigger than 1. No. So in this part, the slope is bigger than 1, but from this point on, the slope is smaller than 1. So we are increasing the contrast for the dark values, and we are decreasing the contrast for the bright values. And actually, that is what we see here. So we should expect a kind of brighter image, because the darker values have better contrast. So if now we compare to the original, now we see that the whole image looks brighter. And again, have we lost information? No, because we can invert that transformation. So given an output value, I would know exactly from which input value it is coming from. So I can invert the transformation, and I have not lost any information. And this is the opposite. So now if gamma, so the expression for the gamma transformation is exactly the same, but now gamma is smaller than 1, and then it has the opposite effect. So it decreases the contrast in the dark values, and it increases the contrast in the high values. So the overall appearance of the image is darker. But for instance, in these areas where the original image was pretty bright, now we have better contrast, and we can compare to the original. So the original image, we barely see the differences of the windows there. But now in the transform image, we can clearly see the contrast, better contrast in that area. Okay, what about gamma correction on the histogram? So let's say that this is the original histogram. Now we have gamma equal 2. So, and now we have some holes here that we understand why we are getting those. And now these peaks, and from the peaks you can also understand why you are doing that, or you are getting that. Because of this transformation, at some point you have to round. So let's say that you have two similar values. Let's say, I don't know, 200 and 201. You apply the transformation, and both are mapping onto a point that when you round, they are getting to the same value. And that is why you're getting these peaks. Actually, this is a very common technique to recognize whether an image has been manipulated or not. So, for instance, let's say that you're as an expert, you are asked, somebody has somebody manipulated this image, or this is just a raw image from the camera, and these holes or these spikes here is a very typical signature of manipulated images. Here is with gamma 1/2. So this is a reminder of what the histogram is, and the histogram just a reminder that it is the probability density function. If you normalize it by the number of pixels, it is an estimate of the probability density function, that if you take a pixel at random, it has that particular value. And we can use that, you can do that for the different bands, so nothing new so far. And you can accumulate that probability density function. And why this is here is because we can use these cumulative distribution functions as transformations, as the lookup table for the point transformation. So here is a reminder, just a reminder of how what these things are. So let's say that you have this image, then you compute, for instance, the value histogram. So you compute the value image, that you know that what it is. It is the 1/3 plus times the red channel plus 1/3 the green channel, and so on. So you compute the histogram of the values, and here is the. This is not the histogram. Histogram is always count. So count is 0, 1, 2, whatever. This is the normalized histogram. Look at the axis. So it is the probability density function. And this capital PDF, or I prefer better this CDF, it is more clear. So this cumulative density function is just the addition of all these values. And remind always the interpretation of that. So the interpretation is the PDF. So the PDF for discrete signal is the probability that that discrete signal takes a particular value g, and then this will be function g, and here we have the PDF. And the cumulative distribution function is the probability that IRC. Remind that the square brackets is for denoting discrete signals. Is smaller or equal g. So this is the sum of gamma, let's say, from -infinity to g, of the probability of IRC taking the value gamma. And this definition is only for discrete signals. So I has to belong to some finite set, not a continuous set. Okay, but if I is a discrete signal, and this is the definition of the probability density function and the cumulative distribution function. And the other day we gave the definitions for continuous signals with integrals, you may remember. Okay, so what we are saying here, is the probability density function and the cumulative distribution function. And the trick is now that we can use the cumulative distribution function, so this one, as a transformation. So now I use a cumulative distribution function is always between 0 and 1, and I want the numbers between 0 and 255, so I have to multiply by 255. And this is plus 1 is simply a trick to, or it's simply telling you that you are using MATLAB and then that you don't have 0 values, 0 indexes in MATLAB. But forget about the plus 1. The important part is this one. So you're using this transformation as your lookup table. So you are multiplying this by 255. So if I have a value 100, then I go to this curve, and this curve is telling me by which value I should substitute in the output image. And this is the same rationale as all these gamma transformations or increased contrast, decreased contrast. So all of them, they look the same. So you have a lookup table, and in this lookup table, you come in with an input value, and then you are told which is the output value for that image, for that point. So it has the same rationale, but only that now the lookup table is defined as a function of the input image. So before, you had the lookup table fixed by your transformation. So you fix first the transformation and then you apply it. But now you look at your input image, then you define your transformation, and then you apply it. So it is a transformation that depends on the input. If the transformation depends on the input, would you say it is a linear operator or a non-linear operator?
It's
Linear. Why?
because everything that depends on something. If you multiply that, the output will be multiplied.
If you multiply the input by 2, for instance, this expands twice, and actually it doesn't make much sense, right? So let's say that you multiply by 2. It doesn't make sense because you are limited by 0 to 55 range. Okay, so let's say that your image is such that it is not, if you multiply by 2, still you are not reaching the 0 to 55, the 255 limit. But then, if I multiply by 2, sorry, so let's say that this is very much concentrated. Then this will have a higher slope. Now I multiply by 2. Now this slope is smaller, right? It is a much smoother curve. So it is not linear. And anything that depends on the input is not linear in general. Think of the convolution. The convolution is a linear transformation, and the kernel doesn't depend on the input, for instance. Okay, so now we may combine different transformations. So, for instance, we can the histogram equalization is defined as the following. So you apply to each one of the input image of the input pixels, you apply this transformation pi. So p is the cumulative distribution function. So they go, every pixel goes through pi. So you see the pixels go, the minimum and maximum values, they also go through pi. And then I transform whatever those values are, I transform them I scale them back to a range that has some particular minimum and some particular maximum. So we recognize already this structure. So we have maximum minus minimum at the output, and then the pixel value minus the minimum at the input, maximum at the input, minimum at the input. So we have the same structure as the one we have here. This one has the same structure, only that now the input is not I, it is I going through the cumulative distribution function. So now, if you think in systems, what we would have is the following. So we would have an input image that goes through the CDF, CDF, and this is what we have called P y of x. And then you go through the contrast tracing. And this is the new image here. And if you compose those two functions, this is what you get. So you would get exactly this expression. Any question? Okay, so this is this idea of using the cumulative distribution function as a lookup table, but now step by step. So let's say that if we have this value image, now we compute the probability density function, and we have here the integral of this one. So this is the cumulative distribution function. And then we transform it, we multiply it by 255. So now we have a lookup table that transforms values between 0 and 255 into values between 0 and 255. And then here is this just an illustration of how regular values or values at the input that are equally distributed, how they are mapped into the output. And looking at this lookup table, this region here where all the values or all the lines almost overlap. So are we increasing or decreasing the contrast in that area?
Decreasing.
We are decreasing by much. That is why they are so close to each other. And the slope here is very small. We can think of it in another way, that is, we are mapping all this area that has almost 100 gray values into an area that has only 20 something or 30 gray output gray values. But now, this is justified because of the fact that between 150 and 250, there are very few values. But there are so few values, so few pixels that take a value between 150 and 250 that we can sacrifice them. So we can compress them. And then this area, that is the one where all the pixels are, we can try to expand the gray values in that area. So here we will have a slope that is larger than 1, and then in this other area where we don't have so many values, we sacrifice the contrast there. But there is no free lunch. The range of values, of gray values that we can use, it is still the same, but we have a more efficient use of those, of that range. So the output doesn't, it is not, the output image is this one, And it is not completely flat, but it tends to be flatter than the original. But it's not completely flat, and we see these holes that now we understand why they are, where they are appearing from. And actually, they should be appearing in areas with contrast increase or decrease. So you would have holes in. So you have holes in this area, but you don't have holes in this other area. Why is that? Because? Yeah, because we are increasing the contrast in this area, so the A we are multiplying is larger than 1, and then it causes this kind of the same effect that we had before. We show it before with A equal 2, but you can imagine it also happens with A equal 1.2 or 1.25 or whatever. So as long as you are increasing the contrast, you are creating holes in the output image. If you are decreasing the contrast, then you don't have those holes anymore, but you have spikes, for instance. And this is always that you have integer valued images. If you have floating valued images, so you can have a pixel with whatever real number you like, then you don't have these holes. Okay, so here is the same transformation, but now with the Luminance image. So we have the Luminance image, the Luminance histogram, the Luminance cumulative distribution function, then you convert it into a lookup table, and then you apply it to the input. Actually, the transformation is not so natural. So we have images whose output histogram is much flatter, so we are using better the range of gray values, but the images, they don't look so natural. So that means that natural images, they don't have equally distributed histograms. So that is one of the properties of natural images. And here we have a comparison of the two, so luminance and equalized luminance. So despite the fact that we have much better contrast here, so for instance, look at these three, you see many more details in the equalized image than in the original image. And the reason is that the difference between maximum and minimum in that part of the image is larger. So we see many more details, but for instance here, the contrast at the house has been sacrificed. This has been this part that is sacrificed by the transformation. And actually it doesn't look so natural. Okay, so let's see this histogram equalization, but now applied to the different color bands. So we have this image, now we have the color histograms, a histogram for each one of the channels, and then the cumulative distribution function for each one of the channels. We convert them into lookup tables by multiplying by 255, and then we can apply it to the original image. But this has another problem, that is, it may create colors that didn't exist. So here we have the two images, the equalized images, and beside the fact that we have kind of a naturally looking image, because naturally looking images, they don't have flat histograms, but additionally, we may have distorted the color relationships between different parts of the image. And we will later learn a better way of increasing the contrast. It is a very, very clever way, I would say. Okay, so we start again from the original image, but now we will apply the luminance equalization, so the equalization of the histogram but only on the luminance channel. So we have the color histogram. Now we have the color cumulative distribution functions. And this will be our lookup table. So our lookup table seems a bit like the ones we were using before. And actually, and you understand now why it looks more, so before we were applying these transformations to each one of the channels. Now we will apply this one to the 3 channels all together. So now, because we have a single transformation, we are not distorting the relative colors, but also, and you understand why. Look at this curve; it is more similar to the green one. So look at it again. You see, it is almost like the green one. So why is that? That the cumulative distribution function of the luminance looks more like the green one. No?
Because you have 2 pixels for 2 green pixels for each red.
No. Because in the formula to calculate the luminance, you may remember that the weight of the green channel was higher than the other 2. So the green was something like 0.5, the red something like 0.3, and the other one 0.1, more or less approximately. So it is the green channel has a more weight on the calculation of the luminance, and that is why the distribution function of the luminance looks more like the distribution function of the green channel. Okay, so now we apply that luminance transformation to each one of the color channels, and it looks better, but still it is not the perfect thing. And probably we can compare to the original one. And we have this saturation point, or more than saturation, it is loss of contrast. So it is this area here. So we have a loss of contrast there. And then we will learn now another transformation, that is this histogram matching. So let's say that you have 2 images, each one with its own histograms, and you want to transform one of them so that the histogram of this transformed image looks like the histogram of the other. And I think that the best way of justifying why we want to do that is by looking at an example. So let's look at the example first, and then we come back. Okay, so now let's say that we have these 2 images. So those are images of the same kind of plant, same kind of garden, daylight, and so on. But for some reason, this image has been degraded. So the colors there are pretty unnatural, while the natural colors are these ones. So can we transform this image to have the natural colors? And this is another example. Let's say that you have 2 cameras pointing at the same point, but because of the different calibrations of the cameras, the same scene looks like this in one of the cameras, and it looks like this in the other camera. And this is a simple calibration issue of the camera. So can I transform these colors into these ones so that I have the same kind of color matching? And this will be the histogram matching operator that we will learn now. So after the transformation, we will transform it into something like this. So it is not that we are manipulating the image in the sense of putting something that is not there, but we are simply compensating for mismatches in the calibration of the cameras. And the same would be with this example. So now we can transform this thing into this one by this operator that we will learn now. Okay, so let's see that operator. So we go to here. Okay, so the trick is to match percentiles. So the cumulative distribution function, if you remember the y-axis, it goes from 0 to 1. So that is a percentile. So it's the percentile of images that of pixels that have a value smaller than gi. And if you compute the cumulative distribution function of an image I and the cumulative distribution function of an image j, then the lookup table will be constructed by matching percentiles. That means, for instance, let's say that I want to know this 5, what is the mapping that I need to do. So I'm trying to construct a lookup table. So when the input is 5, what is the output? Okay, so what I will do is, what is the proportion of pixels in image I that has a value smaller than 5, or smaller or equal 5? So this is 0.65. Okay, so then I go to the other image and compute what is the gray value such that 65% of the pixels are below that value. So 65% of the pixels is below 10. So 5 has to be transformed into 10. Is that clear?
No.
No? Okay. So let's repeat it again. So I want to see, I'm constructing this lookup table where 5 has to be transformed into something. What is this something? So I will look at the input image I. What is the proportion of pixels that have a value that is smaller or equal 5? And this tends to be 65. You have it there, 65. And then I have to look in the image J, what is the value, what is the gray value at which 65% of the pixels is below that value. And that value is 10. So 65% of the pixels in the J image has a value smaller than 10. Actually, it is not 65, it is 67. But it is the first value in J such that 65, at least 65% of the pixels are below that point. So if I take 9, it is only 56, not 65. And if I take 11, it is more, it is higher, but it is not the usual value. So it is the first value, and this is what this is saying. So I have to find a gray value J such that the one before it is smaller than the value I'm looking for, and the one at J, at Gj, is larger or equal the one that I'm looking for. Okay. So this 65 is between 56 and 67. Better now? And you do the same for all the input values. So at the end, you will have a lookup table. So this is just the code to do that. And here is, this is another example. So let's say that we have this image with just 16 intensity values, and this is the probability density function. This is the cumulative density function. We want to match those that histogram to the histogram of this one. So this is the probability density function of the image J and the cumulative density function of J. And then we simply have to substitute or we have to construct an image K such that, or key, K, such that you take image I, you go through the lookup table, and then that is your new image. And this +1 is just a reminder that you cannot have the first index in MATLAB is index 1, while we can have colors of value 0. And here, this is just another MATLAB code for doing this. But this is the transformation, the lookup table. So, for instance, this is the input image cumulative distribution function. This is the target cumulative distribution function. And then you have to make this matching. So, for instance, how many values are below or equal 4 in the input image? And you have 60. And then you have to look for a value in the J image such that you have at least 60% of the pixels below that value. So 4 has to be transformed into 10. And if you repeat that process for all these, for all the input gray values, then you would have these output gray values. And this is your lookup table. Is there saturation in this example, in this transformation? Where do you see this saturation?
From 12 to 15.
Yeah. So 12 to 15 input values, they are all mapped onto 15. So that means that if I want to invert the transformation and I find the 15 in the output image, I cannot know which one of these 4 values were in the original. So there has been a saturation. Okay, so this is more MATLAB, or kind of MATLAB code, almost MATLAB code. And these are, for instance, this is the input cumulative distribution function, this is the output one, and this is the lookup table, and this is what I get. So I get something that is more similar to the target, but it is not exactly the target. So it is like in the histogram equalization. In the histogram equalization, we try to make the histogram flat, but we don't completely succeed. It is flatter than it was at the beginning, but it is not completely flat. Yeah.
¿Es la misma que las anteriores?
Esta es la misma que estas de aquí. Que estas. Esta y esta.
Porque ahora hay saturación por abajo.
¿Por qué ahora hay saturación por abajo? A ver, no me he fijado. No hay saturación.
¿El resultado?
No hay saturación. El resultado. A ver, fíjate, el 0 mapea al 3. Luego, en el input, yo no puedo tener un valor más pequeño que el 0. Con lo que en el output no puedo tener un valor más pequeño que 3. Y luego, el 1, tú dices esto de aquí.
Sí.
Vale, vale. Pues porque el 1 mapea al 7, pero no hay saturación. No hay saturación porque el 0 mapea al 3, el 1 mapea al 7, pero ya está, o al 6, ¿no? O al 6. Vale. Okay, so this was the original image, this is the target image, and now this one has a histogram that is more similar to this one than it was at the beginning. And here we have the same, but now with color bands. So we have the different probability density functions, the different channels, and we have the luminosity probability density function. So that is the black one. And we have the different cumulative distribution functions. And for instance, we have this other image, and with its own probability density functions, the cumulatives, And now we have the one by remapping only the luminosity. So we have used the lookup table coming from the luminosity to map this image into this one, but trying to guarantee that the luminosity of this one looks like the luminosity of this one. And here we have all the details here. So we have, for instance, the luminosity cumulative distribution of the rocket, of the cartoon, and then this is the lookup table, and this is the output. And the output should be more similar to this one than it was at the beginning. Doesn't mean that it will completely make the output to be like the output one, like the target, but it is more similar. And then we can look at the effects of the luminance remapping on the different channels. So these were the histograms before the remapping, and these are the histograms after remapping. So now we recognize in these areas we are increasing the contrast, in these areas we are decreasing the contrast, and that is why we have spikes. And this is the luminance after the transformation. You can look at the cumulative of different channels. So this is before, I think. Yeah, before and after. And now we can try to recover our attempts to do histogram equalization. That we were saying, okay, it doesn't look really like a very natural image. So this was the histogram equalization with a lookup table for each, an independent lookup table for each one of the channels. And this was, all the channels were sharing the same lookup table, that it was the one given by the luminance. But now we can apply the following. So we can do a remapping of what is the distribution function of each one of the bands, and we try to match it to the distribution function of the luminance. Okay, so now that we have learned, actually, I don't know if we have that kind of formula here, but if we don't have it, we can very easily write it. Okay, so let's look at these. Let's look at these pictures. So actually, I will try to make some funny stuff. So let's say that I take this piece, the slide. Now I copy. I can copy it, cancel here, and now I can paste it. So beautiful. So now we can take, let's use a different color. So we have an input value Gi. Okay, so if this is Gi, what is this value? This value is the CDA evaluate of I evaluated at Gi, right? Do you agree with me? And then this value is the same. So this is the CDA of I evaluated at Gi. And now, what is this value here? So this value there is the inverse of this transformation. So this is the cumulative distribution function, but now of the image J. So this point here is the CDF of J minus 1. Minus 1 means the inverse of that transformation. Evaluated at which point? At this point. So I'm going from this Y onto this X. So the inverse has to be evaluated at here. CDF I J. So this point here, the lookup table actually is this one. So the lookup table is this one. I'm transforming this gray value into this other gray value. You see? No? So probably what is more unclear is this thing of the inverse. So if you have a function x and y, and you say have this function y is equal to f of x, what we are saying is if I take this particular x0, I go to here, I find this y0. Okay, what about the opposite? So if the function is invertible, I can go, so this goes in this direction. So first you start with x, and then you calculate which is the y that corresponds to that x. But I could construct the inverse of that transformation. So for instance, I could compute x as a function of y. And then, given one y, I can go to compute what is the corresponding x values. So this inverse should be understood as functional inverse. So for instance, let's write some examples. If y is, let's put it in blue. So if y is the sine of x, then x is the arc sine of y. So it must be understood in that way. And only in the points where it makes sense. So for instance, the sine, truly speaking, is not invertible everywhere. Because the sine is like this. So this is y, this is x. And then if you tell me this y, I don't know if it is coming from this point, this point, this point, this point, this point, this point. So the sine is only invertible from minus pi to pi. And now you understand minus pi. And now you understand why the arc sine is defined in that radius. So we come back to our CDF. So this is what we are doing. So I'm starting with the y, and I'm asking you for the x. So this expression here with the minus 1 is just going in the opposite direction. So in the slides, we didn't have, for that particular slide, we didn't have this expression, but now we have constructed it. But when doing the histogram matching, so the histogram matching is just this tree of computing. So the lookup table is one of the cumulative density functions, and then composed with the inverse of the other cumulative density function. And composed again in the mathematical sense. So you write here. So when you write f composed with g evaluated at x, sometimes you also write it like this. So this is f. Okay, so in our example, we are composing CDF of I composed with CDF -1. Okay. And this is applied to AGI pixel, AGI value. Okay, so that is what is shown here. So it is the CDF of any one of the bands composed with the inverse of the CDF of the Luminance channel, and then multiplied by 255 to make it a number between 0 and 255. And now it is a much more natural looking image. So you can compare, oh, it is not here, yeah, here. So you can compare to the other two attempts that we had. So this was histogram equalization using the Luminance, this, using each one of the channels. This is histogram equalization using the Luminance as the transformation, and this is the one by matching the histograms of each one of the bands to the histogram of the Luminance. And this is the most naturally looking image, and it has better contrast. Okay, so yeah, so here it is a little bit of kind of pseudocode to perform that. And here are some examples. So original color image, original color histograms and Luminance, and then the different transformations, different CDFs, and this is the equalization lookup tables. So the equalization lookup tables for each one of the channels is different because we are matching each one of the channels to the Luminance. So the lookup tables have to be different for each one of the channels. And this is the effect on the output histograms. And here's the result. And for instance, here we can play a lot with all these tools. So for instance, we can take an original image, a target image, and then we can remap each one of the channels independently. So the red to the red, the green to the green, the blue to the blue, and we get this thing here. And well, again, all the CDFs involved and so on. And the effects on the different histograms. But we have already, this is rather repetitive, so we have already seen the main effects. So like creating holes where we are increasing contrast, having spikes where we are decreasing contrast, and the different effects on the CDFs. And here is another example. So let's say that we have two pictures of the same kind of scene, but for some reason these colors have been degraded. And can we match these colors onto this one? So that this is the target, this is the input. And now we know the answer, so we know how to do that. And these are the different lookup tables. And now we have the result here. So the information is the same, but now it looks more like it should. And the same for these set of boxes. And again, all the different histograms and lookup tables, and then the result. Any question? No? Okay, so let's annotate all the possible practices that you can do here. That I have in mind. Compute differences between images. Then we can do histogram equalization. Histogram. This has multiple possibilities like Luminance, color bands, and then we have the histogram matching. Luminance to luminance. Luminance to balance. I think can't remember anymore. And again, be creative. If I have not realized of any practice that you could do, feel free to add it. But I think those are the ones. Let me go back a bit more. I think the gamma transformation we already added. Okay, good. Any question? No? Okay, then we continue with 10 minutes more. So, next lecture is on color perception. So color perception is how we perceive colors. And we are already familiar with this concept that if I want to represent a color, I can do that by adding in, photons of 3 different wavelengths. So for instance, let's say I want to represent a yellow pixel. So what I can do is to take green photons, so photons of a wavelength corresponding to green, photons of red, and then project them onto the same point, and then my eye will see it as green. But in fact, I have only 2 heads, or like 2, 3, 1. This is a different topic. So on the same point, I have 2 different wavelengths. So let's say that this is the spectrum. And the spectrum, you know, you can put it as a function of lambda, that is the wavelength, and this would be density, power spectral density, power spectral density. Now we know it from random signals, right? You know what the power spectral density of the signal is. Okay, so this let's call it S, and we can have it as a function of the wavelength, or alternatively, the same pixel. So this is the pixel, and we are representing now inside the pixel what is the frequency. So we can have what is the power spectral density as a function of the frequency rather than the wavelength. And if I'm not wrong, for photons, we have this relationship. So the wavelength times the frequency is equal to the speed of light. Okay, so if I add photons, red and green photons, so red in wavelength is here, green in wavelength is there. So I never have blue, I never have yellow. What I have is two deltas of red and green photons. But my eye is not able to distinguish those 2 deltas. And what I have is a kind of mixture of red and green that I perceive as yellow. But actually, the spectrum that is being emitted is this one. Okay, this is for when you have a very, very narrow spectrum in wavelength that is called what is the device that emits a very narrow spectrum in wavelength? A laser. So you would have a laser. So what I have drawn here is the spectrum of a laser. In reality, these spectra are never so narrow. And in practice, if you have two bulbs there or two diodes or whatever, so they are more like something like this. So something more like red, something like green, and this is what you get, the emission spectrum that you get. So this would be a laser, and this would be some other diodes or whatever. So, but this is when adding photons, okay? And we have already discussed this idea that when you have a display device, this display device, actually what it has is a very narrow emitters in red, in green, and in blue. Those are those ones having this spectra that I showed before in the whiteboard. And they don't exactly overlap in space. So they are not exactly at exactly the same spatial location, but they are a little bit shifted from each other. And here this shift has been exaggerated so that we can see it. But the thing is that these arrays of red pixels, green pixels, and blue pixels, they don't occupy the same location, but they're a little bit shifted. And then when you look from the distance, then this is what you'll see. You cannot see any longer the different positions of the display of the meters, and you have kind of low pass filter of those in space, but also in colors, because of what we have said, that I cannot distinguish two spectra that are emitting from almost the same point, two lines in the spectrum, red and green. So my eye is not capable of doing that, and I perceive something like this. Okay, so yeah, so if I want to represent an image like this one, all I have to do is to decompose that image into 3 different channels, red, green, and blue, and then compute what is the intensity with which I have to emit in each one of these devices to have the effect that I want at the end. And then I will convert these red, green, and blue channels into currents, and these currents, a current for each one of the emitters. So for each one of these points, I have to compute what is the current that I need, and this current will be given by the intensity at that point in each one of the channels that I want to represent. And here you have the different technologies that you might have. For instance, this is a TV or a screen monitor, a computer monitor, or LCD, and a different setup of LCD. And actually there is a lot of research here, because you can imagine that depending on the shape of the emitters and also the spatial disposition of the emitters, you can save a lot of current. So you can save a lot of energy in trying to display something. Because for instance, this one, it seems that the black area is smaller than in this one. So I have to emit more, I need more energy to display an image here than to display an image there, it seems. So there is a lot of research also on the disposition, the spatial disposition of these things. Okay, then, what about printing? So in printing, and we will revise this idea later, but normally instead of 3 colors, we use 4 colors. So we use not the RGB, we use the magenta, cyan, and another one I don't remember now. And yellow. So it is magenta, cyan, yellow, and black. And the reason for this, and normally we display in this way. So we display, instead of having these arrays, pixels, what we have is this organization, this pattern. Then you print in black ink or this pattern, and you give more or less ink to the different regions depending on what you want to, the effect that you want to have at the end. And then in magenta, you do it in this pattern that is shifted. If this pattern has an orientation of 45 degrees, this one has 30 degrees with respect to this one, and then this one is at 90, 105. And I want to get now into why we are using, we will do it the following day. So tomorrow we will see why we are printing with this, and when we use live, we are displaying with items. But that will be tomorrow. Okay.